Okay, I started to, well, last time one of the things we did was we reviewed some evidence that we've covered so far for atoms. And I pointed out that most of it has come from chemistry in what I've told you so far. And the one exception was this law of heat capacities that Dulong and Petit discovered in 1819. And that, what they found basically was if you took samples of materials that had the same number of atoms, they would absorb the same amount of heat to raise their temperatures by a certain amount. So all the variations in the heat capacities of different materials started to make sense when Dulong and Petit viewed them from the atomic theory point of view and took samples with same numbers of atoms. So that was the first real evidence from physics that matter was made of atoms. And continuing along those lines, studying heat, physicists found a lot more evidence for atoms. So that's what I'm going to be telling you about today and probably next week too. So now let me first review a little bit about heat that I've told you before, just to set the context for this. Remember in the 1700s, there were basically two views of what heat was. One was that it was a fluid. Now this had a certain amount of plausibility to it. Heat does flow. If you take some long object, okay, some metal bar or something, and you heat up one end of it, the heat moves down to the other end of the bar, right? Well, physicists discovered that they could actually describe this flow of heat by equations that were similar to the same sort of equations that describe the flow of fluids. So the fluid theory of heat did have some plausibility to it. Physicists could understand things about heat without invoking any kind of atomic theory of matter. And so a lot of physicists said, well, what do we need atoms for? This fluid theory seems to be working pretty well. But by the end of the 1700s, there were a couple of experiments done that caused the fluid theory of heat a lot of problems. And I think I've already told you about these two experiments, but I'm going to remind you because it was a while ago. The first was done by a guy, Count Rumford. Anybody remember Count Rumford? Okay. Well, one of the things that Count Rumford was a military engineer, and he was involved in making cannons. Okay, so you have to you take this big, cylinder of metal, and you have to drill a hole through it, right? So you can shoot the cannonball through it. So boring out cannons. Okay, well, the way they did this, they would take this big drill and drill through the metal cylinder using horses to turn this drill. Okay, so now what's going to happen when you take some steel drill and you drill through an iron cylinder, Nick? It's going to create a lot of heat. That's what Count Rumford found. In fact, if he immersed this big iron cylinder that he's drilling through in water, it would raise the temperature of the water up to the boiling temperature, and it would just boil off, you know, a whole bunch of water. I mean, as long as the horses kept churning this drill and you kept drilling through these iron cylinders, it seemed to produce an unlimited amount of heat. Now, Rumford asked himself, well, let's look at this from the point of view of the fluid theory of heat. Okay, supposedly, if heat is a fluid, well, you start out with, you know, two fairly cold objects, say. You've got this steel drill, and you've got this big iron cylinder that you're drilling through. And let's say I've got it submerged in a cold bath of water, you know, huge container of water. Okay, everything's cold. I mean, so presumably there isn't much of this fluid heat around, right? Then I start the thing in motion. I start the drill in motion. I start the horses, you know, trotting around. Well, suddenly, you know, a lot of heat is being generated, right? Well, where's it coming from? I mean, if heat is a fluid, I mean, it looks as if this fluid is just being created when it didn't exist before. And it's not what happens to fluids, right? So if heat is a substance, it's really hard to explain what is happening here. Where is the substance coming from? Whereas on the other theory, that heat is just a motion of atoms, well, that theory seemingly does have a way of explaining what's going on here, because what Rumford would then say, you know, accepting the idea that heat is just a form of motion, is that the motion of the horses, okay, is causing, obviously, the motion of the drill. But then that motion of the drill is shaking up the atoms in the drill and in the iron cylinder, which in turn then shakes up the atoms in the water. So what you have is an external motion, you know, of the horses that's being converted to some internal motion of the atoms in the metals and in the water. So you, with the idea that heat is a motion of the internal parts of the metal and the water, you can understand what's going on in this kind of an experiment. Okay? So the idea that heat is a form of internal motion seemingly can explain Count Rumford's results here, whereas the idea that heat is some kind of substance has a lot of trouble explaining this result. So let me see, in your notes, let's just call this background. And number one, Count Rumford's experiments boring cannons. And like I said, this was in 1798. Right around the same time that Humphrey Davy was making laughing gas. Okay, and right around the same time that, let me see, what other famous event have I told you about happened around 1800 in science? Daniel. Yeah, actually, the first electrolysis experiments that were based on the invention of the battery, right? Those were right around 1800. So Now, Rumford, now notice that Rumford doesn't make his result quantitative, or at least not accurately so. He generates a lot of heat. And he actually says in the paper where he wrote this up, he says how much water he was able to boil off and, how much time drilling these cannons and so on. So he does make it somewhat quantitative, but he doesn't actually get a good estimate for how much motion creates how much heat. Okay? Now, why wouldn't he be able to do that? Can you see a problem with his setup? Daniel? Yeah, the problem is, what is his source of motion? Well, it's his horse, right? Now, the horse is exerting some force, but, of course, a horse is a force, of course, but how much force? He's got no way of measuring it, right? So, that's one thing that's missing here, is how, if Rumford's right about heat just being motion, some internal motion, well, then it seems you should be able to prove that a certain amount of motion causes a certain amount of heat. Okay. And Rumford wasn't able to do that. Okay, so let's just leave that as an open question for now. Now, one other experiment that was done right around this time that also supported this idea that heat was motion and not a substance was an experiment that Humphrey Davy did. Humphrey Davy melted ice cubes with just frictional motion. What he did, he knew about Rumford's experiment with the cannons, and so Davy decided to test this, and he thought, well, how can I really shoot a hole in this idea that heat is some kind of fluid substance, and just prove that it has to be motion? Well, he had the idea, what if he has a vacuum chamber, and he's able to put ice cubes, a couple of ice cubes, say, into that vacuum chamber and rub them together. I'm not quite sure exactly how he had his apparatus set up, but if you had, you can imagine if you could devise some, strong little glass container that had, a couple of sealed holes in it or something that you could stick prongs in, and somehow rub the ice cubes together. I'm not quite sure how he managed to do it, but he managed to do it somehow. And sure enough, when he rubbed these ice cubes together, he got them to melt. Now, where's the heat coming from that's melting these ice cubes? There's no air in this chamber. All he's doing is rubbing the ice cubes together. Yeah.
Would it be body heat since he's touching
Well, I mean, that would be something for him to worry about. But presumably he could make the tongs out of, I don't know, some material that didn't transmit heat well. But you're right, that's something he would have to worry about, because what he's trying to show is that where the heat is coming from is just the motion of the ice cubes against one another. Okay, so he's doing an experiment. It's just like, presumably there are highly skilled Boy Scouts that can rub sticks together, right, and start fires. Okay, you've probably all heard that. And actually, highly skilled people can do that. It's not easy, but that's exactly the kind of experiment that Davy's doing right now. Only what he's trying to do, in contrast to the Boy Scout, you see, someone who believed this fluid theory of heat could presumably say to the Boy Scout, well, the heat is coming from, I don't know, the surrounding air, or it's, but Davy's eliminating that. He's saying, and he's submerging this whole apparatus. He's keeping it cold in some, I think, ammonia ice bath or something. So it's like he's done everything he can do to eliminate any source of heat that could possibly get into these ice cubes. And yet, he can still melt them just by rubbing them together. So the question is, where the heck is that heat coming from if it's not just the motion of the ice cubes against one another? So again, this was an experiment that provided good evidence that for the motion, the internal motion theory of heat, as opposed to the substance theory. And this was done, I don't know, around this same time. Let me just say around 1800. Now again, it would have made this would be more impressive and more convincing if Davy could have shown that a certain amount of motion always leads to a certain amount of heat. Troy?
When did Faraday invent the electric motor? Was that 18-something?
Oh, that was, the first electric motors were in the 1820s. Why?
Well, asking you to measure how much motion you put into it to use an electric motor.
How much, so it would be electricity causing motion in the motor.
And then you do that to create heat and see how.
Right, and you would have a quantitative relationship between the electricity and the motion it produces, and so that way you could keep track of exactly how much motion. Yeah, it's a good idea. Somebody thought of that around 1840, and that's the next guy I'm going to tell you about. Okay, so let me see. So you can see that based on this kind of evidence, the idea that heat is motion has really got some basis to it, but it needs to be quantified in order to really be convincing here. Now, one other thing actually that Count Rumford did that was interesting was he thought, well, if heat really is some fluid substance, then if I take an object and I heat it up, okay, well, what are the fluid heat people tell me is happening in this situation? Well, they say that this heat is flowing into this object. That's what's causing its temperature to go up, right? Well, if there's a fluid flowing into this object, it should get heavier, right? Fluid wasn't in it before, is in it now. Presumably, if heat is some fluid substance, if it's any kind of material substance, the sort of substances that we're familiar with, it must have weight. So Rumford actually did that. He would heat up some object. I don't know whether he actually did it with his cannon or with his drill, but anyway, he would heat up some object to some really high temperature and see if it gained weight at all. Weigh it. Found out it didn't. Okay, so again, heat, if it's a fluid substance, it's a special kind of fluid substance that doesn't have weight. So that, again, made the fluid theory less plausible. Okay, so let me tell you about the next guy here that takes these results of Rumford and Davy and makes them quantitative. Nick?
Do people measure electrical fluid too?
Oh,
That kind of
yeah. They did that. They did similar experiments with electricity, and found that when an object was charged up, they couldn't detect any difference in weight. So now that by itself didn't kill these fluid theories, because the people that advocated the fluid theories could always say, well, these particular fluids are so light, our measurements aren't good enough to detect them. So, but it was the combination of all this data that I'm telling you about that really makes the atomic theory convincing. It's not any one little piece. That's why I'm skipping around from chemistry to physics and so on. Okay, well, let's, the next guy to address this whole question of heat and its relation to motion is an English physicist named James Joule. Yes?
Did Chelmsford do the heating experiment around 1800 or?
Yeah, that was 1798. I had that up on the board.
I mean the one where he heated and weighed it.
Oh, he weighed it. Yeah, that was right around the same time. Okay, so James Joule, he was actually tutored by Dalton, the chemist who discovered the law of multiple proportions that we talked about, and then he studied Faraday very closely, and he was a big fan of Faraday's. So he had a thorough background in these ideas that we've been talking about, Dalton's chemistry, and then Faraday's electricity and chemistry. So, and Joule thought that, and of course he knew about Rumford's experiments and Davy's experiment, so he was convinced that heat was some form of motion. And in general, Joule was very interested in what he called conversion processes. the fact that chemical reactions could generate electricity. Electricity could generate motion and heat. And, motion could generate heat. All these different different aspects of nature that scientists were studying, one can be converted into the other. So that's worth writing down. So chemical reactions to, say, electricity, to heat, to motion. All of these, notice that a lot of chemical reactions generate heat, right? If you light a match, what's happening? Yeah.
The question, isn't it chemical reactions to electricity to motion to heat? Because doesn't he believe that motion creates heat?
Well, it could be. You could work it either way. But for instance, you can use heat to create motion too, right? If you heat up a gas in a piston, it'll cause the piston to move. But I'm happy putting it the other way around too. You can create heat directly with chemical reactions. You can create heat with electricity. We've already seen that you can use motion to generate electricity or electricity to generate motion. So all these things are connected. And Joule was interested in investigating these connections. And in particular, he was, Joule was not so much a theorist as he was an experimentalist. He wanted to quantify these relationships, to set up experiments where he could carefully measure, exactly how much motion would produce so much heat, or how much motion would produce how much electricity, which would produce how much heat. Okay, so let me tell you about his first experiment. Let's see, so call this experiment 1. And this was 1840. Now, we've already talked about electrical generators. Remember, Faraday in the early 1830s had discovered that if you take, say, a coil wire and rotate it in a strong magnetic field, okay, the amount of magnetic field lines going through that coil, okay, is constantly changing. And we know that a changing magnetic field through a loop of wire causes a current. Okay, so the bottom line is that if you take a loop of wire, rotate it in a magnetic field, you get this constant alternating current through the loop, right? Okay. That's an electrical generator. Well, here's, and like I said, that had just been discovered by Faraday like 9 years earlier here. Now, Joule has the idea of putting this apparatus together. So you have, let me just call this the generator. Okay, I'm not going to bother to draw which this just means that there's a coil wire in there that's being turned through a magnetic field. Now, let's say the way you're turning that coil of wire in your generator is you've got it attached to a pulley, and you have a weight here that can fall. So when the weight falls, it turns the coil in this generator. When the coil turns, okay, that produces the electricity, right? Now let's say that you've got your wires on either end of your coil coming out of your generator, and they're hooked up to some resistor. Okay, so in other words, you've got these like thick copper wires coming out, and let's say you take a little piece of carbon here, which offers more electrical resistance. Remember we didn't talk a lot about electrical resistance yet in this course, but I did tell you that there's certain materials, like copper, for instance, where electricity flows really easily through them. And then there's other materials, carbon being one, where it will conduct electricity, but it has a lot more resistance to it. Okay, so let's say you put a piece of carbon down here in your circuit. Electricity will still flow, but it has a hard time flowing through the carbon. Now, you stick this part of your circuit that has your carbon resistor into a bucket of water.
Cold water or just water?
Just room temperature water. Say. Now, what's going to happen? Any guesses? Troy.
Well, the water will heat up after you drop the weight.
Yeah, you drop the weight, okay, and the weight dropping causes
Electricity.
the electrical current, okay. The current passing through this resistor heats up the resistor. Okay, I mean any electrical circuit actually. If you take a battery and you just you hook a wire to one terminal and then hook the wire to the other terminal, that wire will heat up. Okay, so electricity causes heat. Now Joule knew this. Now the only reason he's really putting this, I mean you could just put a wire here. Now why doesn't he do that? Dan.
Just to prove that it's not the air and it's nothing that's giving the heat to it. Just to prove that the air is not affecting it.
Well, see, the only heat that he can measure here is the heat that is dissipated in the water, because he's going to measure the temperature rise of this water, right? So Joule's idea is that, I mean, he wants the heat to dissipate in the water. He doesn't want it to dissipate inside the generator or in these wires that are outside the water. So he knows that if he puts the resistor in there, then almost all the heat will be dissipated by the electricity trying to get through this resistor. Okay, first of all, it'll decrease the amount of electricity going through the wire, but it will also, he knows that resistors really heat up, okay, when you have a current through them. So that he's trying to make sure that the heat that is dissipated by this electricity is dissipated in the water. Yeah, okay. Because otherwise, if you don't have the resistor, okay, then the resistance in this whole circuit, okay, where you're generating electricity, it'll all be the same. Okay, so if you have, like, let's say the total length of his wire is, I don't know, let's say it's, he's got like 5 feet of wire, you know, most of it in a coil in the generator. Well, the heat's just going to be dissipated evenly through that whole 5 feet of wire. Not much of that is going to be in his water, right? So he's going to lose most of his heat. So that's why he's got the resistor in there. Okay, so and so he's got an interesting setup here. I mean, you've got the motion of this weight that's causing electricity, which is in turn causing heat. And now he wants to quantify this. Now, so he drops the weight, and he measures the current here. He's previously measured the resistance of this little piece of carbon that he's stuck in here. Troy.
A little bit of the heat still go in the rest of the wire.
Yep.
So how does he measure that?
Oh, he loses that. So he hasn't got a way of measuring that. And that's an error in this experiment. So all he can do is try to minimize it by trying to make sure that the vast majority of the heat dissipates in this resistor. Okay. So, but that is, it's important when you do an experiment to see what the weaknesses of your experiment are, the kinds of things you're not measuring, and the sorts of errors that you're incurring. And so, yeah, Joule knows that he's got a little bit of heat loss in this generator, but he's going to figure out a way around that in the next experiment that I tell you about. Okay, so Joule, let me just cut to the bottom line of what he discovers here. By measuring the current, he's previously measured this resistance Now, how does he do that? Well, I think I told you before that about something called Ohm's law, which is if you have voltage is equal to the current times the resistance in the circuit. So in other words, if you have a battery, okay, that's a 2-volt battery, say, and you can measure. I mean, the resistance of the circuit is just the voltage, so the power of electricity that you're pushing through it, divided by the current. Okay, so if you can measure the current and you know the voltage, you can get the resistance. Okay, so he's got a very accurate thermometer, so he's measuring the temperature increase of this water, and of course he knows what this weight is and how far it's dropping. Okay, so here's what he ends up proving. That the heat generated in this water, okay, that's equal to the change in temperature of the water, right, multiplied by the heat capacity of the water. Okay, so remember when I told you about, okay, this is just review what I've told you so far. This is how he's going to know how much heat he's put into this water. Let's say if it's been raised, if he has 1 liter of water here, and he raises the temperature by 1 degree, how much heat has been added to that water? Did it again. Daniel. Well, 1 kilocalorie actually, because I said 1 liter of water, not if you take if it's just 1 gram of water, okay, which is a milliliter, then it would just be 1 calorie. But 1 liter of water is 1,000 grams, and so that's 1,000 calories. But yeah, that's exactly right. So that's how the change in temperature is related to the amount of heat. Okay, so what he finds, let me see, I'll just state the result now and finish explaining it this afternoon. But he finds that the amount of heat generated in this water is equal to the current squared multiplied by the resistance. And it's equal to the weight multiplied by the height fallen. So he actually gets quantitative relationships between the motion, that's causing the electricity that's causing the heat. And he can relate all three. The heat is equal to the square of the current times the resistance, and that's equal to the weight multiplied by the height fallen. So you can see that by quantifying these things, we're going to see that this is saying a lot more than Rumford was able to say just by, when my horse trots around, things heat up. Okay, so continued this afternoon.